Phase transitions occur when we have changes in the physical characteristics of our substance due to some external factor or combination of factors such as temperature or pressure. Common examples, if we boil water and convert it from a liquid to a gas, or if we condense the gas back into a liquid. So the terms for these, we're probably familiar with the ideas of melting a solid and freezing a liquid. We could also convert the liquid into a gas, which is vaporization. Going the opposite direction is condensation. We can convert a solid directly into a gas without having to go in between the liquid phase. So that's called sublimation. Or if the gas goes directly into the solid phase, that's called deposition. So something like carbon dioxide under normal atmospheric pressures converts directly from solid to a gas. Now, for these transitions, there requires a certain amount of transfer of heat energy under standard conditions. So in order to vaporize a liquid, then that is going to be defined as the enthalpy of vaporization, the amount of energy needed to convert 1 mole of liquid into the vapor phase. Now, if you were going to condense a liquid, then it would be the exact same number except negative. So your enthalpy change would be negative delta H vap here. For melting the substance, then we would have the delta H fusion. And likewise, if you instead freeze the substance, then you're going to have the negative of that quantity. Now, because this number is going to depend on whether you're melting or freezing, you can't get mixed up here on whether you have this definition referring to the melting of a solid or the freezing of a solid. Now, for that reason, you really have to just know these definitions, or you're definitely going to get mixed up on problems. Lastly, we have heat of sublimation. So this is the energy to convert 1 mole of solid directly into a gas. And if we are converting the gas into a solid, then it would be negative this quantity. Now, something interesting about these transitions. During these transitions, transfer of heat energy to the substance does not heat it, nor does taking heat energy away cool the substance. Instead, what happens is that energy goes into rearranging the molecules, or it comes from rearranging the molecules. So for example, if we go from the solid phase into the gaseous phase over the course of sublimation, then that enthalpy of sublimation energy that we are throwing into the system, instead of heating these atoms and going into the energy of their electrons, where most of the thermal energy resides in an atom, instead just goes into pulling those atoms apart in order to put it into a gas phase. Here's a depiction of that occurring for water, for some of water's common phases. We were plotting temperature on the y-axis and the amount of heat energy that we've added on the x-axis. So we start off in the solid phase, and we have this heat capacity for ice. So every unit of heat energy that we add, we go up a corresponding quantity of temperature. Same thing all the way up here. Now, once we get to the freezing point, then now that energy causes no increase at all in temperature. So now that energy is instead going to rearranging these water molecules, breaking those hydrogen bonds and converting it into this liquid phase. And once we've supplied that energy, during which time this substance has effectively infinite heat capacity, then now we're back to the heat capacity for a liquid. So a certain quantity of energy leads to a certain rise in temperature. And this is probably going to be a different heat capacity than we have for the solid in almost all cases. Okay, and now we get to the point where we're going to convert from the liquid to the gaseous phase. The water boils at 100 degrees Celsius. Now again, that energy is instead going into breaking these intermolecular forces. And so there's no rise in temperature until we've supplied that energy. And now we start heating the gas. And again, we have a specific heat capacity for the gas. Let's do an example. Let's ask how much energy are we going to need to heat a 20-gram ice cube from 28 degrees Celsius negative up to 30 degrees Celsius under standard conditions. Well, the first thing we need to realize is that we have to break this problem into 3 parts. And the reason we have to do that is because this is not a continuous curve. If it was all a nice straight line, then we could just solve this problem for that straight line. Whenever we have these breaks of continuity, that usually means that you have to simply split the problem into pieces, because there's not a good mathematical way to model that discontinuity in context of a single equation. So we'll need to figure out this delta H in this region where we are heating the ice. We'll need to figure out the delta H in this region where we are melting the ice. And then we will need to figure out the delta H in this region where we are warming the water. And remember, these are all going to have different heat capacities. So we're going to need to look up the heat capacity for the solid and also the liquid. And we're going to have to do something different here in this middle region. We're going to have to use our enthalpy of fusion because the heat capacity is defined to be infinite in that region. And that's not going to give us good numbers. And note here, it's very important that we get our signs correctly. So we are heating this sample, we are putting energy into it, and you can see that we are going up on the graph, up in temperature and up in energy. And so that means we're going to have positive signs in all these quantities. And we're going to get one large value for delta H at the end. If we were cooling the sample, then this graph would be flipped. We would start up high, go down to this transition point, and then continue down, and the quantities would all be negative. We want to make sure that we're consistent about those. And probably if you ever find yourself adding some quantities and subtracting some other quantities, you've made a mistake. Well, let's start on the first part. We need to heat the ice up to our transition temperature here. So remember the formula for heat capacity. The specific heat of the substance is equal to the change in heat, the amount of heat that you have to dump in, divided by the mass of the substance times the change in temperature that happens when you add that heat to the system. Now for ice here, this is defined to be 2.03 joules per gram Celsius. Now I lied, this isn't actually a definition, this is something that you'd have to look up. And in fact, when you look it up, you'll often find different values, especially in these digits down here. Ice actually, its heat capacity varies quite a bit depending on the temperature that you're at. And depending on your reference, they are probably going to give you a different quantity, depending on which temperature they defined it for. This is good around minus 10 degrees Celsius, and it doesn't vary too much in these quantities over here. But if you have a reference and you get different values, that's okay. So let's go ahead and make this for ice. So all of these quantities refer specifically to the ice that we are working with. And remember, sometimes we're talking about our sample, sometimes we're talking about the system that the sample belongs to. So we have to keep that straight. And we'll go ahead and solve. We're trying to find Q here. And the reason we're trying to find Q is because that can be related directly to our enthalpy. So Q ice is going to be equal to our specific heat capacity for ice times the mass of the ice times the change in temperature for the ice. Something to remember is that when we talk about the change in temperature, or whenever we have these deltas here, we always mean that we take the second value and subtract the first value. That's going to be very important for getting the correct sign in these problems. Remember, we already decided that we're going to wind up with positive signs at the end. If we don't, we've made a mistake somewhere. All right, so we said that this was 2.03 joules per gram degrees Celsius. The mass of our ice cube was 20 grams. And our change in temperature, we're going to take the second temperature. So that's going to be this 0 degrees Celsius times minus our initial temperature, which is this negative 28 degrees Celsius. 0 degrees Celsius minus negative 28 degrees Celsius. Check our units here. So we divide by grams and multiply by grams. We divide by Celsius and we multiply by Celsius. So we get what we want, which is joules. This comes out to 1,136.8 joules. And we'll have 3 significant figures. Since we are multiplying numbers where 3 was the smallest quantity. Now there's a useful trick here, which seems really simple. If we are at constant pressure, then we have this really handy equation that the change in enthalpy is exactly equal to the change in heat energy for our system. So that makes delta H really easy to find now. It's just going to be equal to 1,136.8. And again, I probably could have rounded that to 1,140. But it's usually better if you wait till the very end to do your rounding. That way you don't pick up too much error from the rounding. All right, now let's do this second region where we are melting the ice. Now what are we going to do there since we have this infinite heat capacity? We clearly can't use this handy dandy heat capacity equation. It's not going to work very well if we substitute in infinity for that C value. So what we do instead is we use our enthalpy of fusion, which tells us directly how much energy we need in order to get through this transition based on how much substance we have. Okay, so we are going to melt our ice now. And the heat of fusion for ice, 6.01 kilojoules per mole. Now, sometimes this will be given to you in energy per gram. So you might have to convert into grams or you might have to convert into moles. Now remember, it's very important that we remember the definition of enthalpy of fusion. So what's the definition? Remember, it refers to the melting of the solid. So in that case, our enthalpy of fusion is going to be positive. Now if we are instead forming the solid, so we are freezing our substance, in that case our enthalpy is going to be equal to negative that enthalpy of fusion. And a lot of times when people are doing these problems, they get to this step and they will use the wrong sign here, and then when they add it to our other enthalpies, then that's where things kind of go haywire. So make sure you know this definition. If you don't, you'll get in trouble. And also note that this is for water. All these quantities, they're for specific substances. So if I give you a problem about uranium or alcohol or something, you don't go trying to use these quantities. You'll have to look them up for any of those substances. Okay, well, since we have moles here, that means we also need to know the number of moles of our sample. We don't know that yet because we are given the quantity in grams. So our number of moles is going to be equal to 20.0 grams. And the molecular weight of H2O is that every mole weighs 18.02 grams. So our grams cancels, we get moles. It comes out to 1.11 moles. Now that we know moles, we can make these moles over here go away. We just have to multiply. So our total enthalpy change here, in order to melt this 20 grams of ice, 6.01 kilojoules per mole times 1.11 moles gives us 6.67 kilojoules. Now note here, this kilojoules. Our previous value was in joules. We don't want to accidentally try to add kilojoules to joules. That's another very common error to make in these problems. And by common errors, I mean even I make these errors frequently. It's very easy to get caught up in the next step and forget about these intermediate steps. So go ahead and be careful here. Go ahead and convert this into joules. For the third step, last part of the graph, we need to figure out the amount of heat energy it takes to heat our water. This is basically the same as what we did for the ice. The only difference is that water has a different heat capacity. We use our same heat capacity equation. We're no longer in that troublesome infinite heat capacity region of the curve. And if I solve this for the heat added to water and plug in the values, water has a heat capacity of 4.184 joules per gram Celsius, something you have to look up if you don't know. And our sample was 20 grams. And remember, delta T, we take the second temperature, which is that we heat this up to 30 degrees Celsius, and you subtract the first temperature. We're starting at 0 degrees Celsius because we just finished melting our ice and converting it to water. All right, so multiply this all out. Grams should cancel and Celsius should cancel. We get 2,510.4 joules. And as long as we are at constant pressure, then we have that the enthalpy change is also equal to the amount of heat added to our system, which is again 2,510.4 joules. Now the very last step is that we need to add all of those enthalpies together. So our total enthalpy here, we figured out that we would need 1,136.8 joules to heat up our ice to the transition temperature. We calculated we would need another 6,670 joules in order to melt that ice. And lastly, we would need 2,510.4 joules in order to heat the water that we have formed up to the desired temperature of 30 degrees Celsius. We add this all together, we get 10,317.2 joules. There should wind up being sig figs to the tenths place. That's our limiting decimal position in this addition. We could call this 10.32 kilojoules of energy. Yet another important way of describing phases is by phase diagrams that relate the phase to the present pressure and temperature of the system. Now do note there's no convention on which goes on which axis. So sometimes you will see this diagram flipped with temperature on the y-axis and pressure on the x-axis, and that's fine. Now it probably makes sense to you that if you have a very high pressure, that the atoms are going to be packed together and you'll have a solid. Or if you have a very low temperature, then those attractive forces dominate. And so then we have a solid. Or conversely, if we have a very high temperature, then the atom's molecules have the opportunity to disperse and exist as a gas. Same for very low pressure. Then in between is where we have our liquid. Something interesting here is this point right in the middle. This is called the triple point. Now at the triple point, all these phases can coexist. Earth has an average temperature of about 15 degrees Celsius, and that's fairly close to the triple point for 1 atmosphere of pressure. Of course, the pressure varies across the different parts of the Earth and its atmosphere. And so that's why you see water as ice and as water, and also as cloud vapor. It's pretty interesting. Don't really see other substances existing in all three phases. Something else unusual. So we said we had to cross this boundary. This is called the phase boundary in order to get between one phase and another phase. But that's not quite true, because I could go ahead and increase the pressure of my liquid, and then I could increase its temperature, and then I could decrease the pressure again, and I would be over here in the gas phase without ever having to cross this boundary. So this cutoff point right here, this is called the critical point. And this region up here is called a supercritical fluid. Now this is a phase in between liquid and gas phases, which has properties of both. All right, so these supercritical fluids, they pick up some important features being in between gases and liquids. They can dissolve materials like a liquid. So an example of a practical application of supercritical fluid is you use supercritical carbon dioxide, and it's capable of dissolving caffeine. So you do something horrid, you add it to your coffee beans, and it dissolves the caffeine, and then you can just let it evaporate, convert back into a gas phase by reducing the pressure, and that will deposit your caffeine, and so you'll have decaffeinated coffee beans, and you can do something else with the caffeine. Something else that supercritical fluids can do is they can effuse through solids like a gas. So, for example, how air escapes the walls of a balloon, that's something that supercritical fluids can do. Because there's no gas or liquid boundary, then there's no surface tension. They're just as happy being a liquid as they are being a gas, because they're both. And they have other properties, which are in between those of gases and liquids. So for example, density and viscosity, you can see that the values for supercritical fluids lie directly in between those for gases and liquids.